In a vector space, it's common to use orthonormal bases to represent the elements of this space. In this video, we will define a basis for a vector space, and we will present the Gram-Schmidt process to obtain an orthonormal basis for a given space. A basis for a Hilbert space of a given dimension D is a subset of D vectors of this space, a subset of vectors that allow to represent every element in the vector space as a linear combination of these elements of the basis. The coefficients for this linear expansion are unique, and in many cases they are called the coordinates of this vector. A basis is orthogonal when every pair of elements in the basis are orthogonal, and this means that their inner product is 0 for every pair of elements in the basis. And an orthogonal basis is orthonormal if the energy of every element in this basis, the norm of every element in this basis, is 1. Taking into account the relationship of the norm with the inner product, this means that the inner product of an element of the basis with itself is equal to 1. Orthonormal bases are very useful because the coefficients of the linear expansion, the coordinates, can be easily calculated using the inner product. The coordinates for a given vector x are given by the inner product of x with every element in the basis. As simple as that. The main objective of the Gram-Schmidt orthogonalization procedure is to obtain an orthonormal basis that allows to represent all the elements in a vector space. In particular, we will apply this procedure to the obtention of an orthonormal basis allowing to represent a set of M signals, because we will apply it for the M signals that are used in a digital modulator. We have M signals, S0, S1, up to Sm-1, and from these M signals we will obtain an orthonormal basis of dimension n that will be lower or equal than the number of elements in the space, and we'll use the notation phi0, phi1, and up to phi n-1 to denote the n elements of this orthonormal basis. For continuous time signals, the definition of the inner product that is appropriate for the purpose of the design of a digital communication system is the integral of the product of the first signal times the second one complex conjugated in the case of complex signals. Taking into account this definition and considering the properties of an orthonormal basis, the inner product between phi j and phi k will be 0 for every pair of different elements in the basis, and the inner product of an element of this basis with itself will be equal to 1 to have an orthonormal basis. With this definition of the inner product, the norm of a given element is equal to the square root of the inner product. This is equal to the square root of the integral of square modulus of the signal. This is the definition of a square modulus of the energy. And this means that norm equal to 1 is equal to energy of the signal equal to 1. With these definitions, now the inner product allows to obtain the coordinates for the signals in the vector space by means of the inner product between the signal and every element in the orthonormal basis, and with these coordinates, every signal can be written as a linear combination of the element of the basis. And therefore, a given signal can be represented by the capital N coordinates that represent this signal in the vector space. To obtain the orthonormal basis from the signals, the Gram-Schmidt procedure has the following steps. In the first step, we need to choose one of the signals, S0 of t, and the first element of the basis is just the normalized version of this signal. The signal is divided by a square root of its energy to guarantee that phi 0 has unit energy. In the next step, another signal, S1, is selected. Then it is necessary to obtain the projection of S1 in the element of the basis that we have, phi 0, by means of the inner product. And we obtain this coordinate A1, 0. Then we convert S1 in an orthogonal function with respect to phi 0. This function is called D1, just by subtracting to S1 the projection of this signal with respect to phi 0, coordinate with respect to phi 0 times phi 0. And then D1 is normalized by dividing it by the square of its energy to guarantee that phi 1 has energy equal to 1. And this procedure is repeated with every signal. When we process Sk, maybe we have previously k elements in the basis, phi 0, phi 1 up to phi k minus 1. First, we need to compute the coordinates of Sk in all these elements of the basis by means of the inner product of Sk with every element of the basis. Then the signal dk is constructed by subtracting to Sk the projections of this signal in all the previous elements of the basis, each coordinate times each corresponding element of the basis. If after the subtraction of all these projections we have a null signal, this means that it is possible to represent Sk as a linear combination of the elements that we have in the basis, and a new element of the basis is not necessary to represent this signal. Otherwise, the last step is just normalization. dk is divided by the square root of its energy to guarantee that phi k has energy equal to 1. This is the Gram-Schmidt procedure that allows to obtain a basis of dimension n to represent m signals.